Okay, so let us try to look at the following system. X dot is equal to -1, -2, 0, 0, x plus 1, 0, u. Let us say that this is our open loop system. And actually this is one of the systems that we have solved an example for. Okay? So I have this system, and now let us try to look at the open loop poles. This is a open loop, okay? What are the eigenvalues of this matrix? -1, -2. How do we know this?
S minus.
If you are calculating S minus Si minus A here, then it's an overkill. Okay? So for diagonal matrices, for lower triangular matrices, for upper triangular matrices, eigenvalues are always the diagonal elements. Okay? You don't really have to calculate those, calculating Si minus A. So we see that the open loop poles are at -1 and -2. Suppose that I don't like these open loop poles, and I would like to change their position. Okay? I can actually try to bring them to more to the left of the complex plane. Okay? So in this case, I can think about state feedback. Let us choose our K as K1 and K2, and let us try to change the open loop pole locations to closed loop pole locations. So I have a closed loop is equal to A minus BK, and that is A is -1, -2, 0, 0, minus B is 1, 0, and K is K1, K2. Okay? And then if I calculate this matrix, it's going to be K1, 0, and K2, 0. And when I do this subtraction, then I will obtain the following. -1 minus K1, and I have minus K2, and I will have -2 and 0. Okay? Where are the closed loop poles?
-1 minus K1 and...
The eigenvalues are the diagonal elements. Okay? The closed loop poles are at -2 and -1 minus K1. Okay? By choosing K1, I can change this closed loop pole location. But K2 really does not change anything. Okay? And the other eigenvalue, the other pole remains at -2. Okay? So do you think I can bring the poles of this open loop system to -3 and -4? Can I bring the open loop poles to this closed loop poles? So we see that sometimes we cannot do this. By choosing any K, we will not be able to do this actually. The sufficient condition for being able to do this all the time for any closed loop pole location. Can I bring the pole locations to -3 and -2? Yes, I can just bring this to -3 and then to -2. So some pole locations are still allowed for me, but some pole locations are inaccessible. Okay? I will not be able to do it for using any K. So sometimes when your system does not have controllability, you will end up with this type of situation. Okay? This system was not controllable. We have actually solved an example for this. Q for this system is 1, 0 and -1, 0. Determinant is 0. It is not completely controllable. That is why when I try to apply state feedback, I cannot place my closed loop poles arbitrarily in the complex plane. Okay? So this is not going to happen when we have controllability. So that is actually what we are going to write here. Let us write theorem. If the open loop system x dot is equal to ax plus bu and y is equal to cx is controllable or completely controllable, then the poles of the closed loop system, which are the eigenvalues of a closed loop, which is a minus bk, can be placed arbitrarily. In the complex plane by choosing a suitable k vector with state feedback. This is called pole placement. So placing the eigenvalues at the desired locations by using a suitable k vector is called pole placement. So when we have controllability, we now have such a case. We will be able to play with both eigenvalues at the same time, and we could place them anywhere we like. So let us look at an example for state feedback design. We have x dot is equal to, I have 0, 1, 0, 0, 0, 1, and 0, minus 6, 5, x, plus 0, 0, 1, u, and y is equal to 2, 2, 1, x. Find a state feedback rule. Feedback rule. This is going to be in the form u is equal to r minus kx. By finding a state feedback rule, we mean finding k. Okay? Find k such to place the closed loop poles at s equals to minus 1, minus 2, and minus 3. Okay? This is the task. So in general, this task is going to be quite easy. I will not be I will not be calculating any determinants, anything like that, to calculate the eigenvalues. The reason is that compare this thing to this state space representation. What can you say about this state space representation? It is in controllable canonical form. When the state space representation is in controllable canonical form, design task is going to be really, really simple. Okay? So in this case, we have a system in controllable canonical form. Okay? In this case, I can actually write the open loop transfer function immediately without calculating any SI minus A's, any inverses. I can write the open loop transfer function of such a system by inspection. Okay? So let us write the G open loop of S. Let us try to write this. In the denominator, I will start with which term? S cube. And then I will have what? Minus 5 S squared plus 6S. This is my denominator of the transfer function. Okay? So I just looked at the last row here. Minus A1, this is the transfer function. Minus A1, minus A2, and here. And n here is the size of this matrix. Okay? And then I can write what the numerator is. It is going to be S squared plus 2S plus 2. Okay? So what is this? This thing is actually, this is determinant Si minus A itself. Okay? This is actually, this denominator is the characteristic polynomial of this A matrix. We see that I didn't calculate Si minus A, I didn't calculate determinant, okay? But I could write the characteristic polynomial of that matrix by looking at only its last row. Okay? So when A matrix is in that form and B vector is in that form, it's going to be really easy to write these determinants or these Si minus A inverses, etc. You don't really have to calculate them. You can write the transfer function by inspection. So now let us try to apply this design. So here I see, where are the open loop poles? I have S squared minus 5S plus 6 here. Where are the open loop poles? One of the open loop poles is at 0. The other ones are at 2 and 3. So what can you say about the open loop system? Is it stable? No, it is unstable in Bebo's sense, meaning that this is also a stabilization task at the same time. Okay, by using state feedback, we are trying to apply stabilization as well, and we need to place the closed loop poles at these locations. So now let us try to do this. I will calculate the closed loop A matrix. A closed loop is A minus BK here, and A is given there. Minus B is 0, 0, 1 times K is going to be K1, K2, K3. Okay? So now let me calculate this matrix first. It is going to be 0, 0, K1, 0, 0, K2, 0, 0, K3. And then I will subtract this matrix from that one, which is going to give me the following: 0, 1, 0, 0, 0, 1. And I will do this subtraction. Minus K1, minus K2 plus 6, minus K3 minus 5. Okay? It is just this matrix, which is the closed loop A matrix. And now I need to place the eigenvalues of this matrix at minus 1, minus 2, and minus 3. By choosing K, I need to place the eigenvalues of this matrix at these required positions. So what do I need for my characteristic polynomial? D of S should be at the end. It should be S plus 1, S plus 2, and S plus 3 multiplication. S plus 1, plus 2, plus 3. This is called the desired characteristic polynomial. Okay? This is desired characteristic polynomial. So let me say that it is D bar. That is the desired characteristic polynomial for this matrix. Let me write the actual characteristic polynomial of this matrix. Okay? It is D of S is, with which term am I going to start? Characteristic polynomial would always start with S to the dimension of the matrix. It's going to start with S cubed. Okay? And then I will continue with which term? Compare these two matrices. How you wrote the denominator here. It's the characteristic polynomial of this matrix. This matrix is exactly in the same form. Only the last row changed. Okay? So I could read the characteristic polynomial of this matrix by looking at its last row only. And I could do the same thing for this one as well. Without calculating any determinant, without calculating any Si minus A, I can write the characteristic polynomial of this thing. S cubed, and then what? Plus K3 minus 5, K3 minus 5, S squared, plus K2 plus 6S, plus K1. Okay? That is the actual characteristic polynomial of the closed loop system in this case. And then what am I going to do to get these eigenvalues? I will expand this polynomial, and the desired polynomial is going to turn out to be the following. It is S cubed plus 6S squared plus 11S plus 6. Okay? Then if I want this polynomial to have the same roots as this one, all I have to do is to equate the coefficients of these two polynomials. Okay?
Hocam bir şey sorabilir miyim?
Yes.
Controllable sistemlerin hocam, o normal unit feedback var ya yaptığınız her zaman. O bakımdan bir farkı var mı aslında?
Unity feedback sistemleri.
Evet.
Tam şu anda alakasını kuramadım. Yani herhangi bir sistemi olarak yazar. Yani feedback architecture hakkında bir şey söylemiyor bize aslında. Controllable canonical formda olması.
Controllability bizim şu anki farkına varmadığımız başka bir şey değiştirmiyor değil mi?
Yok. Evet, aynen öyle. So here, all I have to do now is to equate the coefficients of those two polynomials. So K3 minus 5 is equal to 6, meaning that K3 is 11, okay? And I have K2 plus 6 is equal to, the next coefficient is 11, meaning that K2 is 5. And finally, I have K1 is going to be equal to 6. Okay? So that actually means that for this system, the state feedback rule is u is equal to r minus k is 6, 5, 11 times x1, x2, x3. Okay, or if I write this explicitly, minus 6x1 minus 5x2 minus 11x3. Any questions? So now let us solve an example for which the system is not in controllable canonical form. System not in controllable canonical form. In this case, we have the system x star is equal to 1, 2, 0, 0, 4, 1, 1, minus 5, 0, x, plus 0, 1, 0, u. Y is equal to 3, 0, 1, x. Design a state feedback rule. U is equal to r minus kx. This means that I need to choose what k is, such that the closed loop poles are all located at s equals to minus 1. Okay. So now this is really not included in the design, but I can check if this system is controllable or not. I see that the system is definitely not in controllable canonical form. So I can try to check whether it is actually controllable or not. But that is not included in the design step, okay? So here, let us check whether this is controllable or not. I have Q is equal to B, AB, and I have A squared B, okay? Q is 0, 1, 0. And if I multiply this with this one, what am I going to get? It's going to be the second column, 0, 4, 1. Okay? And if I multiply this with this one, I will get here 1, and I have 16 minus 5. It is, 11. And I have 4 here. Okay? And now I have to calculate the determinant. Okay? Should I choose this column to calculate the determinant? So if I choose a row or column which is filled with non-zero elements, I will have to calculate lots of determinants. Okay? So that is why I usually choose columns or rows which contain as many zero elements as possible. Let us try this one. I have plus, minus, plus, plus here. Okay? So then the determinant of Q is going to be this element plus 1 times the determinant of the remaining matrix when I remove this row and this column from here. And the 1, 4, 0, 1. And this is going to be 1, which is non-zero, meaning that this system is controllable. So in this case, definitely I know that the state feedback problem has a solution. Okay? It is not an infeasible problem anymore. I know that I need to be able to find K1, K2, K3 values, which is going to place the eigenvalues at these desired locations. So now I can look at my design. So I will calculate here the closed loop A matrix. A closed loop is A minus BK. And here A is 1, 2, 0, 0, 4, 1, 1, minus 5, 0 here. Okay? And I have minus, B is 0, 1, 0. And I have here K, K1, K2, K3. And when I do this multiplication, I will get 0, K1, 0, 0, K2, 0, 0, K3, 0. Okay? And now let us try to do the subtraction. It is 1, 0, 1 and 0, 1, 0 here. And then I will subtract the second rows. It is going to be minus k1 minus 2, minus k2 minus 4, minus k3 plus 5. Okay? Now I have to place the eigenvalues of this matrix all to the desired locations, s equals to minus 1. So then, what is the desired characteristic polynomial? D bar of s, desired characteristic polynomial. What is this for this example? Yes? It is s plus 1 cubed. It is s cubed plus 3s squared plus 3s plus this one. Okay? And now the task is to find the actual characteristic polynomial of this thing. Now, unfortunately, there is no shortcut. Okay? So I need to do this the long way. D of s is going to be a determinant of si minus a closed loop. Okay? So that is why I need to calculate si minus that matrix. All right? So si minus a closed loop is going to be, I will have s minus 1, 0, minus 1, and I have k1 minus 2 here, and s plus k2 minus 4, and I have k3 plus 5, and s minus 1 and 0. This is si minus a closed loop. Okay? So now I have to calculate the determinant of this thing. How should I do it? Choose this one, this one. Yeah, let us choose this. Okay. So here I will put plus, minus, plus. Okay. And then let us try to calculate this determinant. So I have d of s is equal to, I will take this element first. It is s. And then I will take the determinant of the remaining matrix when I remove this row and this column. Okay? It is going to be s minus 1, and I will have here s plus k2 minus 4. Okay? It is this quantity. And I have minus, there is a minus sign here, there is a minus 1 here, so they are going to cancel each other. And then I'm going to remove that column and that row. Okay? I will remove this one from there. And I'm going to get the following. I have s minus 1, k3 plus 5, and I have minus, there is a minus 1 here, plus k1 minus 2. Okay? So I will write the result here that we are going to get from this. It is s cubed plus k2 minus 5s squared plus k3 minus k2 plus minus plus k1 minus k3 minus 7. Okay? That is the characteristic polynomial of the closed loop A matrix. So now all I have to do is actually, I need to equate the coefficients here. So k2 minus 5 should be 3, meaning that k2 is equal to 8. So k3 minus k2 plus 9 is going to be equal to 3. k2 is 8 here, so this is k3 plus 1. So k3 is equal to 2. And finally, I will k1 minus k3 minus 7 is equal to 1. So is k3 is equal to 2 here. This is minus 9, so k1 is equal to 10. Okay. That completes the design. Yes. Efendim? That is the desired polynomial. So here, in the question, we need to place the closed loop poles at s equals to minus 1. Okay? So here, this desired characteristic polynomial would determine that. If I equate this thing to 0, then all of the characteristic polynomial roots will be at -1. Okay? And that is why I choose my characteristic polynomial to be equal to s plus 1 cube.
Küçük olmasının altısı koyduğunu anladım.
Yes, exactly. So if I were designing this thing as for a system with state dimension 25, then I need to equate that thing to s plus 1 to the power 25. Okay?
Hocam,
Yes.
en başta işte sistemin kontrolünde olduğunu gördükten sonra kontrolün bu forma çevirip çözecek ne olur?
You can actually do that with a state, with defining a new state. Okay, so after calculating the transfer function, you can come up with a state feedback gain, and there is also a design. If you would like to do this in a computer, that is what you do. Okay, so when you get this type of, when MATLAB gets this state space representation, and if it would like to design a state feedback rule for that, it first converts this into controllable canonical form. It designs the k parameters. Then it transforms those k parameters back into this state space representation. Okay, that is how the computer design is actually made. And for higher order systems, that is the only option.
Hocam, for both systems, k values will not be the same, right?
No, they will not be the same.
Hocam,
Yes.
K değerleri negatif gelebilir mi?
Yes, there is no problem in that. Bu k değerlerinin negatif olması ile ilgili böyle çok bir çekinceniz var gibi ama ya bu çekince bende yok yani. Neden öyle düşünüyorsunuz bilmiyorum. Yani şöyle, k'yı negatif koymak pozitif feedback anlamına geliyor esasında. Output feedback'te baktığınızda pozitif feedback'e çevirmiş oluyorsunuz sistemi. Her pozitif feedback'in sonu unstable bitecek diye bir durum yok. Öyle sistemler olur, bazen sadece negatif k ile stabilize edilebilirler. Aslında öyle şeyler olabilir. Yani sisteminiz şuysa ne yapacaksınız? -1 bölü s artı 1. Sistem buysa zaten negatif k kullanmam lazım ki stabilize edeyim ben bu sistemi. Ki şu -1'i buradan yok edeyim. Tamam ya, saçma bir sistem. Çünkü DC gain'i falan negatif. Yani siz ona 1 verince -1 veriyor output'u. Yani bu sistemi feedback loop'un içine koyduğunuz zaman tabii ki negatif k ile ancak yapılabilecek, stabilize edilebilecek. Çünkü o negatif k ile şu -1'i yok edeceksiniz aslında ve de öyle stabilize olacak. Yani k'ların negatif olması ile ilgili bir problemimiz yok.
Hocam,
Yes. No, that is actually what I'm going to do now. Okay, I will now try to find the open loop transfer function. It's not included in the design, but I'm just going to be showing it. What is the open loop transfer function of such a system? Let us try to do it. When I look at the open loop transfer function, I will calculate it as follows. The open loop of S is equal to, I have C times Si minus A inverse times B. Okay? So, and we know that this is going to be written as C times adjugate of Si minus A times B divided by determinant of Si minus A. Okay? Then for calculating the denominator, I will calculate Si minus A and then its determinant. Si minus A is S minus 1, 0 minus 1, minus 2, S minus 4, and plus 5, and 0, minus 1, and S. Yeah. Okay? So now let us try to calculate this thing. I have plus minus plus. Burada artı eksi falan, artı eksi artı falan koyuyorum. Bunu anlıyor mu herkes? Ne yaptığımı? Plus minus plus, minus plus minus. There is something in determinant calculation. Okay? These coefficients are always coming. It is minus 1 to the power I plus j. I is the row number. J is the column number. That is what you do in determinant calculation. Okay? And then the determinant of such a matrix is going to be determinant Si minus A. The denominator here is going to be S minus 1 times I have S squared minus 4S plus 5. Okay? So that is the first term. And then I have minus one here, okay? And then I will have the determinant of the remaining matrix. It is just 2, okay? Minus 2. This is going to give you the denominator, all right? I think you can continue with the rest. Well, denominator is, finding numerator is more problematic here. So here, let us try to find the numerator. Okay. When I try to find the numerator, I need to calculate Si minus A, the adjugate matrix. So if you would like to calculate the inverse of such a matrix, this is ABCD. It is adjugate of ABCD divided by, I have determinant of ABCD. Okay, that is the inverse of. So that is what I did here. This matrix inverse is this ratio. Okay, and when you try to do that, you write the determinant AD minus BC. That is the determinant, and the adjugate becomes change the places, change the signs. Okay, DA minus B and minus C. Okay, so we see that for a 2 by 2 matrix, adjugate of the matrix is the following. Adjugate of ABCD is equal to DA minus B minus C. Okay? So how can we come up with an adjugate of a 3 by 3 matrix? This is a 3 by 3 matrix, and I need to come up with it as adjugate in order to be able to calculate the numerator of that transfer function. Okay? So here let us try to understand what this operation is. If I would like to find the first row, first column of the adjugate matrix, I have a D here. Okay? But D is the following element. I remove this row, I remove this column and this row, and the remaining determinant is D, and I write it here. And for finding this A, I remove this row and this column, and I have here this A, the remaining matrix determinant is here. If I do the same thing to an off-diagonal element, okay? If I want to find minus B, okay? If I remove this row, remove this column, the remaining determinant is C, and there's a minus sign. So I should write here minus C. So the idea doesn't work here. Okay? Why did it not work? So here, let us try to do it for this matrix. A, B, C, D, E, F, and H, I, J. Okay? So let us say that I would like to calculate the adjugate of this matrix. Okay? This is going to be a 3 by 3 matrix, and it's going to be formed out of some determinants. Okay? This is plus minus plus, minus plus minus, plus minus plus. If I would like to calculate the adjugate matrix elements for the diagonals, what I do is the following. I remove this row, this column, and the remaining determinant becomes my adjugate matrix element. It is E, F, I, J. Okay? And if I would like to calculate this element, it is going to be again a plus sign. On the diagonals, I always have plus signs. Okay? So I will have plus signs here. Okay? Then if I remove this row and this column, I will get AC and HJ. And finally, for this one, I have AB, DE. Now, if I would like to obtain the adjugate matrix, an off-diagonal element, what I do is the following. It is not going to be the following. If I would like to obtain this element in the adjugate matrix, I do not write this matrix. I remove this row and this column. Okay? It is going to be minus, a minus sign is coming here. Okay? It is not going to be DFHJ. Okay? This is actually wrong. Okay? Let us try to see it here. This is ABCD. Okay? I need to obtain minus B at the end. Okay? This is plus, minus, 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 plus here. Okay? If I would like to obtain this element, I remove this C from the matrix. Okay? I delete this row and this column, and then I write here minus B, okay? And then if I would like to obtain minus C here, I remove this and this instead, and I write minus C here. So for off-diagonal elements, what I need to do is that instead of writing it like this, I need to remove this row and this column. Bunu anlatabildim mi? Çok evet, aynen öyle. Yani bunu bu şekilde hesaplarsanız, bu hesapladığınız matrise kofaktör matrisi deniyor. Tamam mı? Algebraic matrisi kofaktörün transpozu. So if you do your calculations in this way, by removing the corresponding element and its corresponding column and corresponding row, the matrix that you calculate is called the cofactor matrix. Okay? The algebraic matrix is the transpose of the cofactor matrix. That is why, if you would like to calculate this element here, you need to remove the element in its conjugate, in its transpose. Okay? You need to remove this row and this column from here, and the remaining matrix is going to be the one that I need to calculate the determinant. Okay? So if you would like to calculate this element of the aggregate, you need to remove the element in its transpose. I need to remove this row and this column. Okay? I need to write here minus because of this minus sign, and it would be BC, and I would have IJ. Okay? And if I would like to write this element, it's going to be plus, and I need to remove the element in its transpose. Okay? So this one is going to be removed, and this one is going to be removed. So I will end up with the determinant of BCEF. Okay?
Hocam şu en baştaki okulun formülünü nasıl yazmıştık?
Bunu mu?
Evet.
Bunu genel bir sistem için yazdık. Şöyle. X dot is equal to AX plus BU. Y is equal to CX ya. Bunu Laplace transforma geçirelim. Sx eşittir Ax artı Bu. Buradan x'i U cinsinden çekebilirim. X eşittir S eksi A inverse çarpı U oldu. Tamam. Şimdi bunu şurada y'de yerine koyayım. Y eşittir C çarpı x'miş. C çarpı şurada B kalacak hala. S eksi A inverse Bu oldu. Şimdi y bölü u'ya bakarsanız bu transfer fonksiyonun ta kendisi. Okay? So now let us come back to our problem. The numerator. So the numerator here is C times adjugate of Si minus A times B. C for this example is 301. Okay? I will have here the adjugate matrix. Okay? That is the adjugate matrix of Si minus A. So this is adjugate of Si minus A, okay, times the B vector, 0, 1, 0, okay? This is my numerator, all right? In order for me to be able to calculate the numerator, which elements of the adjugate matrix do I need? This multiplication is going to give me the second column, okay? This multiplication, it's going to be related to the first row and the third row, okay? So which elements do I need? This element, let me say it's alpha, and this is beta, okay? The other elements, 348'de don't care hala böyle mi gösteriyorlar? Değişmemiş. So here this is going to be 3 alpha plus beta, okay? So the only elements that I need to know in the adjugate is these two elements, okay? So now let us calculate those elements, okay? So here I have plus, minus, plus again. So alpha is going to start with a minus sign, and then I will write a determinant, okay? So in order to calculate that element, alpha, I need to remove this element from my matrix, okay? I need to remove this thing, this row and this column. And then I need to write the remaining matrix determinant. 0, minus 1, minus 1 s. Okay? So this is going to be just 1. Alpha is equal to 1. Okay? And beta is, what I need to do to calculate beta is to remove the following. To calculate beta, I will remove these ones, okay, in its transpose. And it is going to give me, the beta also has a minus sign, I think, so it is plus minus plus here. It also has a minus sign. And I have here s minus 1, 5, and I have 0, and I will have here 0 and s. 0. Efendim? Ay evet. Son saatte böyle oluyor. Beta is going to be, there is a minus sign here, and I will have s minus 1, 0, and 0, minus 1. Okay? So we see that beta is s minus 1. Okay? And then the denominator is going to be 3 times alpha, 3, so this is 1. This is 3 plus beta is s minus 1, that is s plus 2. Alright? That is the numerator. Yok, siz yanlış hesaplıyor gibisiniz. Neden? 0 eksidir. Bir de burada eksi var.
Eksi artı, eksi değil. Eksi bir çarpı eksi bir değil.
Hocam son saatte sonra.
Evet, son
Yani ben de kötü durumdayım. Okay. The only thing remaining here is the observability. Okay. That is a simple condition that we are going to see, and it is a necessary condition for being able to design an observer in an easy way or in a satisfactory way. What we want at the end is that this is my state space system. X dot is equal to ax plus bu. Y is equal to cx. This is the input and this is the output. For applying state feedback, I need the whole state, okay? But for getting the whole state, I need to measure them somehow. I really do not want to put additional sensors into my system. That is why sometimes we choose the observer method. That means that we measure only the input and the output of the control system, and we give it to a computer. Okay? In the computer, I can assume that I can solve any differential equation that I would like to solve, any linear differential equation. So by taking this u and this y, we can design a differential equation which is going to give to us an estimate of the state. This is called x hat. Okay? So my aim here is that this x hat should converge to this actual state x. So we want here x hat to even if at the beginning they are not the same, I want x hat to converge to x at the end as t goes to infinity. That is what we want from an observer. And after getting that state estimate, instead of feeding the actual state, we can try to feed its estimate back. Okay? Then if this estimate converges to the actual state sufficiently fast, then the control system would behave really nicely without even measuring the actual state.
Hocam ya bunun kendi lokusu var mı?
Efendim?
Kendi bir lokusu var mı? Yani o pollara giderken izlediği bir yol. Yoksa direkt oraya gitmiş mi olur?
In general, what we try to do is the following. We define an error. Okay? This error becomes x hat minus x. Okay? We define this error, and after designing the observer, we end up with the following equation. X dot is equal to a observer times E. We usually establish our observer equation so that this error behaves like this linear system where I have a new A matrix here that is called A observer. And we try to place the eigenvalues of this observer A matrix to as left in the complex plane as possible. Okay? So for example, what we do is the following. If I want my state feedback controller poles at these two locations, we place these observer poles much to the left. Okay? So these would become our observer poles. Observer poles. These would be our controller poles, or closed loop poles. Okay? So when we place the observer error poles to the left of the closed loop poles, we know that this convergence becomes exponentially, and the time constant of that convergence would be related to the real part of these poles, and the frequency of convergence is going to be the imaginary part of these poles. But here, by placing the observer poles here to as left as possible, we guarantee that this convergence happens much faster than the time that is necessary for the controller to work. We actually establish this convergence to be faster than how our closed loop system would be working. Okay? And this convergence becomes exponentially, and the time constant of the convergence would depend on this A matrix that we choose, and then that we design, and then the error can oscillate, and the frequency of that oscillation would be determined by the imaginary part of these poles. Okay. That's all for today. Thank you very much.
Hocam sınavda observability var.
Observability var ama observer design yok.
Hocam bir şey söyleyeceğim. Burada kompütürden çıkan X'in daha sonra X'e konverjilmesi, K'ye feedback bulutuna geri verilmesiyle alakalı mı? Yani bir şey söyleyeceğim. Ben mesela gereksiz bir sistem tasarladım. Hem X'i ölçüyorum, hem kompütürle X'i hesaplıyorum. Ama X'e feedback olarak değil de X'i